Alright, these are notes 511, and we're going to start by kind of going through what we worked through yesterday to find new identities. So these are nice little, technically these will eventually be double angles to you, but for today what I want us to do is use our sum and difference identities from yesterday to kind of rewrite these and expand them. So the idea is sine of 2x, so that's really the same as sine of x plus x, and using our identity I can expand that, I'm going to look at this guy right here, into sine of x cosine of x plus cosine of x sine of x. The commutative property of multiplication tells me that I can take this guy and rewrite him as the red version. So now I have two of these, so twice sine of x cosine of x. Equivalent expression. So I can take this sine of 2x and simplify it down into that nice little identity, or replace it, and that's what we're going to work with today. The next thing we're going to do is the same thing with cosine. So cosine of x plus x equals cosine of x times cosine of x, subtract sine of x times sine of x. And that's going to be the double angle identity for cosine. Now what's neat about cosine is hopefully you kind of recognize, oh, you got this cosine and this sine squared business going on. What we can actually do is we can take our Pythagorean identity that we learned earlier in the chapter. And let's say I want to get rid of cosine for some reason. So I'm going to solve the Pythagorean for cosine, and then take this business and put it in for cosine squared. So 1 minus sine squared of x minus sine squared of x, and that turns into 1 minus 2 sine squared of x. So there are times where maybe we have cosine of 2x, and this is going to be a nice substitution for us to take care of, and that's what we'll do. The other thing we can do is maybe we decide that we want to get rid of this sine squared of x. So now I'm going to have this cosine squared of x, subtract, instead of sine squared of x, we're going to say 1 minus cosine squared of x. This is going to go in and become, distribute that negative through. So this is 2 cosine squared of x minus 1. So that's another identity that we could use instead. So cosine square, or the double angle identity for cosine, really has 3 different substitutions you could make. This is the technical one that I usually just memorize this one. These two come from Pythagorean substitutions. Not anything too crazy. These are the double angle identities that we are going to work with today. We just did sine and we just did our cosine as well. I didn't make us do tangent, but this is the double angle identity for tangent. You will need to memorize at least this one, and this one for your test. And like I say over here, there are 3 identities for cosine of 2x, the double angle identity for cosine. They work. You're going to see that you have to use them. There's different places where one's going to work better than the other, and that just kind of comes with practice. But generally, if you remember this one and you know your Pythagorean identities, you can do that kind of quick substitution off to the side to kind of get through that. Nothing too crazy. This is going to be the first problem that we work through. Erase all this, you're going to act surprised. This is solving equations using your double angle identity. We're going to solve these on our usual interval of 0 to 2 pi, and here are your double angle identities hanging out over here for you. The first thing is these both have sine, which is good. This is a double angle, so we go ahead and replace this as twice sine of x cosine of x equals twice sine of x. Get everything to one side, so we're going to set this equation equal to 0. From here, this is going to be a form of factoring, and we're going to think about trying to just factor out something they both have in common. They both have 2, and they both have sine of x. So 2 sine of x comes out. We're left with cosine of x minus 1 equals 0. So we're going to set both of those expressions equal to 0. So this is going to be sine of x equals 0, and that happens at pi and 0. And this is going to be cosine of x equals 1, and that happens just at 0. So our answer would be 0 and pi. This one's a little bit trickier. It's not as straightforward, but it is one that can definitely be done in just a few steps. The idea is you need to solve this expression again. Unfortunately, it has a double angle, so we're going to definitely do that substitution. So we're going to say twice sine of x cosine of x minus tangent of x equals 0. Now this one said equal to 0, which is a good thing, but I don't have any common terms that I can factor out. So what I decided to do is, instead of writing tangent as tangent, I wrote tangent in terms of sine and cosine because that's what I had in my first term. So tangent turns into sine of x over cosine of x. And from here, I went ahead and tried to create a common denominator. So my denominator is going to turn into cosine, so I multiplied this by cosine of x over cosine of x. So that became 2 sine of x cosine squared of x minus sine of x all over cosine of x, still equal to 0. So this is using some of the proof techniques as well that we kind of used later. And the idea that, well, I have two things, let's combine them into one, it'll be easier to solve. When I look at the top, they both have a sign hanging out, so I'm going to take out a sine of x. On the inside, I have 2 times cosine squared of x minus 1 all over cosine. Hopefully what you're kind of thinking is this we can take out, set that equal to 0, and then this portion, set that guy equal to 0. This is really tangent of x. So tangent of x is 0 in 2 places. It's 0 at 0 and pi. This guy, cosine squared of x equals 1. Divide each side by 2. And then take the square root. We're going to rationalize it, unless you're starting to recognize that guy. And then we don't want to forget, because we took a square root, plus or minus in front. So whereas cosine of x equal to plus or minus radical 2 over 2. This is a 45-degree reference angle. And we're doing the plus or minuses, so we're doing every 45 on your unit circle, one rotation around. And there they are. For this one, what we need to do is we need to fix the problem. So go ahead and put a 2 in front of that cosine squared. Typo on my part. And this guy, we have cosine squared of x, we have cosine, and we have cosine of 2x. We have to pick which one would be the smartest for us to use. I'm going to look at the left-hand side. And as I'm looking at the left-hand side, everything is in terms of cosine. So I probably don't want to bring a sine squared in, so I'm going to focus on using that middle substitution. So we have twice cosine squared of x plus cosine of x equals twice cosine squared of x minus 1. From here, I'm going to take away cosine squared of x from each side. I'm really just trying to get all of my terms on the same side. But when I make that first leap, this goes away, and I'm actually left with a really nice expression. Cosine of x is equal to negative 1. That only happens one place. Remember, cosine's your base, so it's going to happen at pi. This next little bit isn't the prettiest, and it kind of seems weird how we're going to prove this double angle identity. It's kind of a proof in a way again. The idea is I want this side to be rewritten to match the right-hand side. So we have to use double angles. I probably wouldn't want to bust out cosine of 3x plus 3x. I probably would get there, but we are in the double angle set of notes, so that's why you probably lean towards using double angle. So if I want to turn the left into the right, if I'm looking at my three possible substitutions for cosine, my right-hand side has cosine squared and sine squared, so I'm probably going to lean towards using that one. The hardest thing for us sometimes is rewriting this as a double angle, so I want cosine of 2 times something. 2 times something would be my 3x. So this is my double angle. You can think of this kind of as being your x. This is going to simplify down into cosine squared of 3x minus sine squared of 3x, and that's equal to the other side. That's it. And I think I'll do a new video for this one, because this guy just has quite a few steps.